reasonable. Okay, we're going to start out with looking at the uptake of LDL. And those things. This is, I think, what really the Nobel Prize in Medicine was all about, was the discovery of the uptake of LDL by the liver. It's about the only cell that can take up LDL. Okay, you know LDLs from what? What's your context with LDLs? It's bad, yeah, considered bad cholesterol. LDLs have been floating around in your bloodstream for days, and about the only cell that could possibly want them or pick them up is the liver. Okay, so there is an LDL receptor. So the LDL, I don't remember. Okay, consists of a layer of phospholipids surrounding a blob of fat. Okay, so for lack of a better word, and there is a protein. There's a drawing of LDLs. ApoB. Okay, that will bind to the receptor. So the LDL receptor is going to bind to ApoB, or I should say ApoB binds to the LDL receptor. And it binds with actually fairly low affinity. That's why LDL circulate in your bloodstream for a couple of days, because sometimes the contact between the LDL, the ApoB on the LDL and the receptor don't really hit it off, and so the LDL just kind of bounces off. Okay, LDLs came from a bigger, this is what the liver makes. Okay, just imagine this going all the way around. Okay, and what the liver makes is a bigger mess. Okay, so when you get bored, you can finish up your picture. Okay, but this is what the liver makes. It's called a VLDL. For very low density lipoprotein, and this is an LDL. So the liver spits out VLDLs. Okay, and they circulate through the bloodstream, and I think they have about a half-life of 6 hours or so. And as they circulate through the bloodstream, there are enzymes on skeletal muscle cells that can pluck out the triglycerides from the middle. So this is made up of triglycerides, a blob of triglycerides, and cholesterol, but there's more triglycerides than cholesterol. So as the VLDL is circulating, some of the triglycerides are pulled out, and the skeletal muscles can use them, because as you are sitting here right now, your muscles are producing predominantly fat as an energy source, not glucose as an energy source. And so endurance training involves getting your muscles to use fat as an energy source at higher intensities of exercise. So triglycerides are really important for your muscles. Okay? ApoB has a high affinity for the LDL receptor, and I'm sorry if this is not quite on the video. So a lot of times the VLDL gets picked up by the liver, and it gets repackaged so we can keep getting those triglycerides to circulate. Okay? But eventually, ApoE is lost from the from this VLDL, and you're left now with ApoB, which has a fairly low affinity for the LDL receptor. But it's the only thing that the LDL receptor can interact with. Okay, and so that's why LDL persists for a couple of days, because they have such low affinity for the LDL receptor. And because triglycerides have been taken out, by the time you get to an LDL, the cholesterol is more abundant than the triglycerides. You didn't add cholesterol, it's just that the triglycerides were removed, but nobody wanted the cholesterol. Okay, so that's sort of a little bit of context for the LDL. Okay, so I'm trying to make the LDL. Okay, so the LDL receptor, let's have the LDL receptor bind to an LDL, and I'm going to make the LDL yellow. Okay, and I need to go back and we'll take a look at the C-terminal amino acids on the LDL receptor. So when an LDL binds to the receptor, in this case the receptor kind of falls into a pit that's being formed by clathrin. Okay. And clathrin then picks up will enclose and coat the entire vesicle until it gets pinched off into a vesicle. Okay, then ARF, because an ARF is controlling the coating and uncoating, ARF hydrolyzes its GTP. Okay, so that's ARF doing that. You end up with an uncoated. Oops. So now we've got the LDL receptor and the LDL in the cell. This is going to fuse with an endosome. Okay, so there's going to be a fusion there, and I think there is even the RAB has been identified and the Wiesners have been identified. So this is a fusion, and we end up with something that kind of could be shaped like this, or it could have many branches. Okay, it could have it could look like a star with all these really thin vesicle branches hanging out. This has a couple of names. It can be called a sorting endosome. It could be called an early endosome. So I've looked at a whole bunch of figures today because this is a slightly different version than the picture, than that article I gave you a while back with the internal compartments. Okay. But this seems to fit most of the things. This used to be called, when receptor-mediated endocytosis was first discovered, this used to be called a curl. So its old name is a curl. And it stands for the compartment for the uncoupling of the receptor and the ligand. The compartment of uncoupling of the receptor and the ligand. Because it kind of tells you, because it was short, it's sort of shaped like a curl, but it also told you what in the heck is going on. And because it's slightly acidic, the LDL gets dropped off from the receptor, okay? So we lose the affinity. It gets even worse between the LDL and the receptor. Okay, so the LDL gets dropped off. Now the receptor has to go someplace, okay? And it's got a couple of options. It could go here, okay, somewhere around here, or it could go here, okay? Which has more surface area? The real long strangly thing, right, has more surface area, okay? So it's low here, because this is almost, it's a sphere. You can't get a lower surface area, or a smaller ratio of surface area. And over here, it's high. So where do you suppose the receptor is going to end up? Yeah, just by probability, it's going to end up in the region where there's a lot of surface area, so we can kind of squeeze. Okay, so I had a squeeze, we'll squeeze the LDL receptor in the area where there is high surface area. So it seems like there's no sequence separate, that selects the LDL receptor at this point. It's just going to, by probability, and land in the compartment with a huge surface area, and that would be that little extension thing. LDL is going to remain in the area where there's a high volume, and it's certainly not this thing. This thing has pretty low volume, so we're going to end, the LDL will just stay here. Okay? So this thing could hinge off to form a vesicle. No clathrin, no COP1, no COP2, it just is going to form a vesicle, and it will return to the surface. Okay, so that's one possible fate. This is the most direct fate. Is that skinny little thing will pinch off, and we'll move the receptor back to the cell surface, and then that receptor can be used again. Okay, so they I think labeled some LDL receptors to see how many times could it take this pathway, and the average LDL receptor can do about 300 cycles, which is a lot considering it's probably getting a little beat up down here in the acidic zone. Okay, so that's one pathway. Another pathway, and I'm going to try to leave it on the board, and I hope it can be seen on the video. Another pathway is that it could end up in a vesicle that fuses with something that sort of looks like trans-Golgi but isn't. This is called a recycling compartment, or endosome. Let's call it recycling compartment. Okay, so and this is a second route back to the plasma membrane. Okay, is that pretty cool? I remember when this used to be extremely complex. I'm thinking, man, this is about the easiest pathway we've seen in a long time. Okay, but I'm going to give you some sequences of the LDL receptor. Okay, so the LDL receptor, if we kind of blow this region up and look at the C terminus, let me do this in here. In fact, I'm just going to take it out. And here's the adapter protein, and it is not APC. You look at the C terminal sequence, what would you find here? It is okay. So what you need to notice is, oh man, I haven't got these bulky hydrophobic amino acids again. We got phenylalanine and the tyrosine. So it kind of follows the same pattern. But this is also important, okay? The asparagine and the proline together. So that's its address label. And there's lots of proteins with that address. Well, no, there's not. I think it's pretty unique to LDL. Take that back. It's unique to LDL receptor. Okay, so the C terminus is, the sequence would be there. I'll draw that in. So we have F, D, N, P, V, Y, okay? And there's a particular adapter protein that recognizes this and only this. I think there are a couple others that have that. Okay. So like I think I said earlier that this takes a very little bit of time. It takes about 15 minutes for an LDL to bind to the receptor and for the LDL receptor to make it back out to the cell membrane to pick up another one. So you can imagine if this was going like constant cycling, and you have 300 cycles, 15 minutes per cycle, and again, and it's probably not going quite that fast. That protein persists for quite a long time before it has to get replaced. Okay, I hope you guys have enough room to put in another protein. Can we load this compartment up one more time? Okay, let's do it. One more protein. So here's a situation where the ligand is going to, by the way, we haven't dealt with the ligand. So this, what's left over, becomes a late endosome. So this pinches off. This compartment just matures into a late endosome, becoming increasingly acidic. And then the late endosome matures into a lysosome. And the LDL is degraded, so the phospholipids are broken down. The protein ApoB is broken down. The cholesterol, you have to really break down cholesterol. Okay. The liver might reuse those components, reuse the lipids to build another VLDL to send out. Okay. So here's the situation where the receptor is recycled, but the ligand that the receptor brought in is going to be degraded. Okay? So that's one story. The other story is the transferrin story, where both the ligand and the receptor are going to be recycled. Okay, so they're going to, it kind of sounds really odd, but both this receptor and the ligand will get recycled. So let's choose a couple new colors. Okay, so we're gonna have, a transfer and receptor here in green. And transfer will be red. Okay. So transferrin's main job is to transport iron ions through the bloodstream. So the transferrin has a capacity to bind to 2 irons. Okay. Iron, and it's in the okay, it's in the charge on the iron is +3. What kind of amino acids do you think is in, would you find in transferrin? Probably negative charged amino acids, so aspartic acid and glutamic acid. Okay, so when the transferrin is carrying 2 iron, it's called ferrotransferrin. And at neutral pH, ferrotransferrin binds fairly well to the receptor. And I'll give you the values of the dissociation constant in a bit. Okay, so a transferrin receptor loaded with a ferrotransferrin binds to a clathrin-coated kit, and so this is receptor. And the transferrin receptor, I think I gave you yesterday, is Y. Okay, so tyrosine, any 2 amino acids, and a bulky hydrophobic amino acid, phenylalanine is a bulky hydrophobic amino acid. Okay, so it binds to, transferrin receptor binds to AP2. Okay, LDL receptor has a different adaptor protein that it binds to. And there are probably then, is in this figure, that in this thing that's forming, multiple adapter proteins so that receptor-mediated endocytosis can take in a bunch of different things, not just one type of a thing. Okay, so transferrin receptor gets in. With its cargo, the ferrotransferrin. Right? We uncoat the vesicle. We arc hydrolyzes its GTP. Okay, and I have to change my curl shape to accommodate what's happening here. I'm going to put a little bump here. To hold on to the. Okay. So once we get to the acidified endosome, in other words, the sorting endosome or the early endosome, okay, the iron loses its affinity for the transferrin, okay, or we could say the transferrin, it's probably more correct to say the transferrin loses its affinity for the iron at acidic pHs, so the iron ions come off, and now we have an empty transferrin, still bound to the receptor because at acidic pHs, this receptor has a high affinity, okay, for the ferrotransfer, for the empty transferrin. Okay. So this is called apotransferrin. Once the two ions have been dropped off, the empty transferrin is called apotransferrin. In other words, it's just kind of, it's just like a bare naked transferrin. Nothing, it's not complete. There it is. Okay? And the affinity at this pH is 6 times 10 minus 9 moles. That's extremely high. So at 6 times 10 to minus 9 moles of the transferrin, 50% of that's going to be bound to the receptor, 50% is not. But look at the minus 9. I mean, that is an extremely small value. So apotransferrin at its pH of about somewhere between 5 and 6 has a very high affinity. There's a high affinity between apotransferrin and transferrin. And it's about the same up here. I did 6 times 10 to the minus 9. Okay. So it doesn't take much ferrotransferrin to glob onto the transferrin receptor. It's a very high affinity between the receptor and the ligand, and that is actually a classic characteristic of receptor-mediated endocytosis, that the binding between the ligand and the receptor is very high, the very high affinity. So it doesn't take much. You know, there could be very few ferrotransferrins circulating in the blood, but when it makes contact with the transferrin receptor, chances are it's going to stick. Okay, so what's going to happen to the apotransferrin then? It's going to make it all the way back to the surface. Whoops. I have to put in, I forgot to put in the green receptors, so let me draw those in. So by the time we get out here, and we're out on the cell surface, the transferrin, apotransferrin, is going to dissociate because it essentially has absolutely no affinity for the receptor at a neutral pH. Okay, so this is this story followed. It became clear following the LDL receptor mediated endocytosis, and then it became clear that, well, gee, not always is the ligand degraded. Sometimes it is recycled, and here's a case where the ligand is recycled. So scientists have used different, these proteins, the LDL receptor and the LDL, the transferrin and the transferrin receptor to mark various compartments, as markers for various compartments. Okay, for example, you would never find a transferrin in a late endosome, but you'd find an LDL in a late endosome. Okay, you would find transferrin in here where you wouldn't find an LDL, okay? So sorting, recycling compartments would contain transferrin, but they wouldn't contain LDLs. They would contain both the LDL receptor and they would contain the transferrin receptor. So these have been used as markers to identify different compartments. But the problem is there's so much interplay between the compartments and they're constantly in flux that there's only a few really compartments that can actually be identified by particular markers. Okay, one more detail, and I'm going to move the detail over here, okay, only because I think it's not getting picked up by the video. I'm going to redraw the recycling compartment, okay? And then we are going to have an official end of the unit. Okay, here's our recycling compartment. It might contain an empty LDL receptor or a bunch of them. It could contain some transferrin receptors and transferrin, okay? And this is a hideout for GLUT4. You remember GLUT4? Okay, this is the hideout for GLUT4. One of the two hideouts. Okay? In fact, GLUT4 seems to vacillate between two compartments. This recycling and then a storage vesicle. And somebody, a lab has been able to watch GLUT4 go back and forth between these two compartments. So when there's no insulin present, this is what happens to GLUT4. It vacillates between the recycling endosome or compartment and the storage vesicle, back and forth, and back and forth, and back and forth. Okay? Once insulin is present,